Good evening, everyone. Mechanics of Materials, Chapter 5, Torsion, Torsion of Non-Circular Members. So we want to see if we do have a rectangular plate handling a torsional torque at both ends like T and T prime. We want to calculate a shear induced due to this torsional torque if we extract an piece of element from that plate, like what is tau maximum in this piece of element. So if we have a rectangular cross section with the width of A, thickness of B, and length of L, handling two torsional torque at its both ends in different direction, tau maximum can be obtained from this equation: T torsional torque over C sub 1 and coefficient times width of plate times thickness squared. And likewise, a angle of torsion is TL over coefficient of C sub 2 times width of plate times B cubed times shear modulus. And B is nothing but the thickness of the plate. And this table coefficient for rectangular bars in torsion, so or plates. It just shows us the ratio of the width of our plate to the thickness of plate, and if it's all the way to the and it's equal to 1, C1 is 0.208 and C2 is equal to 0.1406. And as soon as you move toward the thinner plate, you can easily see C1 is increasing all the way to the very, very thin plate like infinity. And if you look at the pattern of C1 and C2, they are increasing as your plate goes thinner and thinner. So we replace these coefficient like in our equation. If our ratio, for example, if A over B is equal to 0.2, you just move to this table and pick these two coefficients in calculation of tau maximum and phi. That's the formula for non-circular or rectangular plates in terms of shearing stress in torsional torque. The other category is like thin-walled hollow section. So the either in circular shape or rectangular shape. By thin walled, we do mean that any of these section can be hollowed section because there is no nothing inside. There is R1 and R2 and also dimension. And the reason we call them thin walled, it's when your radius or dimension, like here, it's at least 10 times the thickness of your plate. So either radius bigger 10 times than or equal to T, or dimension of your a L or width over the thickness. That's why we call it like thin vault. So we can say every thin vault section is a hollowed section, but not all hollowed sections are thin vault, because that's upon based off the ratio of dimension to the thickness. And if they are handling a torsional torque of T, we want to see in this scenario what is the shear induced due to torsion. And this time the equation is a torsional torque over 2a sub m times the thickness. And a sub m is the area average, area inside plus area outside over 2. It just gives us, and the visual of that is if you just have a circle, like a dashed red circle between R1 and R2, that's like a average. The same concept also applies for this rectangular one. It's something, a center line goes all the way through the rectangle, and also effective polar moment of inertia is 4 times a average squared over integration of ds over dt, closed integration of dimension over the thickness in a closed circle. And also phi is again like TL over GJ and we have to replace effective polar moment of inertia for hollowed section in this equation. Let's put it into an example to see how it works. So in our example, we do have a structural aluminum tubing of 2.5, rectangular shape of 2.5 times 4 inches in dimension. So this is length 4 inch and width 2.5 inches with a thickness of 0.16 inches, handling a torsional torque of 24 kip inch. And if the thickness, wall thickness all around is 0.16, we want to know what is the shearing stress induced due to this torsional torque. So we can move to a 10-volt hollowed section because definitely 4 or 2.5 is really bigger than 0.10. 0.10 times 16 is 1.6 and the smaller one is 2.5. So definitely it's 10-volt hollowed section. Tau shear is equal to torsional torque over 2 area average time the thickness, and AM is A in plus A out. It's like if you just draw a dashed line circle between the two uh, out and in. So out is all the way 4 inches and there is a half of that you have to subtract it from here, half of the thickness there. So it says 4 minus 1 thickness from the length, and the same because the in the other direction always 2.5 inches and the thickness, a half of the thickness goes subtracted here, the same value and half of that. So it just says 2.5 minus a thickness and it just gives us 3.84 times 2.34. It gives us 8.986 inches squared in terms of A average. And as soon as we have that, we are plugging in AM to our equation, and that's a like easily you can get your tau value, which is tau is equal 8.75 kilopound the square inches. We'll solve more problem. Thank you.